We've seen a couple of examples of utilizing high-dimensional grid. And for example, invariance construction free of three-term arithmetic progression into in the Euclidean plane, n by n grid, finding a subset of points without corner. In graph theory, we are doing this early Rothschild problem on constructing a graph whose edges are all triangular edges, meaning that they lie in a triangle with positive edge density, but no large book. And we've also seen how to use high-dimensional grid to construct a graph that's almost complete, but there's holes everywhere, meaning that we can decompose the edge set of this almost complete graph into induced matchings of size almost linear in the order of the graph. So today we're going to move on to a different type of geometric construction utilizing so previously the high-dimensional grid, the interesting counterintuitive property is that for almost all pairs of points, they are around a typical distance apart, which is definitely not true in this three-dimensional world that we live in. So today we're going to move on to a different high-dimensional object, high-dimensional sphere, and show that there's also some very strange counterintuitive properties of high-dimensional sphere that we can make use of. Can you guys see my screen?
No.
No.
No? Okay. 1 second. I haven't started writing. Good. Let me try it again. Can you guys see it now?
Yeah.
Okay. So today we're gonna see, as I said, how we can utilize high-dimensional spheres. Okay. We're gonna see some classical examples and some recent variations, recent developments. So the classical example where we use this high-dimensional sphere is in this Ramsey-Turan type problem. So let's briefly recall the Ramsey-Turan problem. So first, in Turan type problem, Turan theorem, if you recall, we have an n-vertex graph. Let's say KR free. Then the maximum number of edges, if you have this G, is attained when G is this R minus 1 part type graph. Right? You partition the vertexes into equal parts, R minus 1 parts. In particular, there is a huge holes inside this graph. There's a linear size independent sets. So you have alpha of G is linear in N, a large hole. This prompt motivated Vera Short in the 70s to ask, what if our host graph is not so structured? What if we forbid linear size independent sets? Then how much we can improve these bounds on Turan's theorem? So Schorsch asked, so problem. I'll just write like this. Schorsch asked, what happens if no large independent sets? And she was mainly interested in the regime where alpha of G, the host graph, has sublinear independence number. So the simplest case is triangle free. For triangle free, let's compare. You have a m vertex graph G, which is triangle free, R equal to 3. In the normal world, we have Mantel's theorem, and we know the maximum is complete bipartite graph, which has n squared over 4 edges. Now, if we require here additionally, alpha G is little o of n, then we claim that the maximum E of G, it cannot have positive edge density. It drops to little o n. Why is that true? Simply notice that in triangle free graph, for any vertex V, so here's a proof. In triangle free graph, the maximum degree is bounded by the independence number, which is little o n. So if maximum degree is little o n, you have the edges. This will imply this. Okay? Simply because for every vertex, its neighborhood is independent set. Otherwise, you have a triangle. So we see already a huge improvement. The maximum drops from n squared over 4 to little o n squared. Edge density drops from 1/2 to 0. The next case turns out to be a lot more difficult, which is the K4. So this K4, first non-trivial case. Which is K4. So let's give a formal definition. Okay, let me not give the definition for now. So familiarity first proved that an upper bound proved that for any n vertex graph G, if it's K4 free, and in this case also independence number is sublinear, then the number of edges, so without this condition, we should have complete tripartite graph, which is n squared over 3 edges. So now we have at most n squared over 8 plus some error term. Let me write in terms of density. Okay, let me just write like this. Okay, at most n squared over 8. We proved this last semester, so I'll skip the proof. We will see for a while, it's not clear whether there exists a dense meaning positive edge density, K4 free graph with sublinear independence number. This was proven to be true only about a couple of years later in this surprising geometric construction, which is the one utilizing this high-dimensional sphere by Bolobach and Erdős. So Bolobach and Erdős matching lower bound. So that there exists an M vertex graph G, which is K4 free. Alpha of G is little o of n, and E of G is 1/8 minus little o1 n squared. Okay. So let's go through this construction. The construction is geometric. Construction idea. The vertex set of the graph, let's say G is VE. So what do we want to do? This is what we want to do. We want a K4 free sublinear independence number and lots of edges. Okay, these three property. The vertex set of G consists of two copies of high-dimensional sphere, and we have n vertices. So you throw n half vertices uniformly over one sphere, and n half vertices uniformly over the other sphere. So we have these two. Let me move things a little bit. So as I said, the vertex of V consists of X union Y, where both X and Y they are isomorphic to high-dimensional sphere, real sphere. This is X and Y. Now you uniformly random, they uniformly distribute vertices over the sphere. Do the same here. Okay, and have vertices on each side. This is just a sketch, okay? Let's not worry about details for now. How do we make the adjacency? There are two types of edges. Inside edges, those are living completely inside X, living completely inside Y, or cross edges with one end in X and the other end in Y. So for the inner edges, let's start with inner edges. So for inner edges, we say that X is adjacent to X prime if and only if they are almost antipodal. Antipodal. Okay, so you have X. Oh, you have X here. You have X prime here. You add an inner edge if they are almost at the opposite position inside this sphere. On the sphere, antipodal position, almost. There's some little room to wiggle. This is how we add inner edges. So this guy is only adjacent to a small spherical cap here. Let me draw it. This is like the neighborhood of X. Is that clear? Ask question in the chat if you have a question, if anything's not clear. Now, for the cross edges, we also define it geometrically. So for X and Y, let's say you have Y here. Let's say you have Y prime here. Two cross edges Let me use red. Cross edges. X adjacent to Y, if and only if. Now you imagine X and Y lives in the same sphere, and if one lives in the hemisphere center at the other. So so this is Y, right? And we're gonna imagine X and Y lives in the same place. So this is like Y here. And you look at the hemisphere around X. So hemisphere around X means this. Oh, maybe let me draw it this way. I would draw a copy of X here. Oops. Imagine X and Y live in the same place. Let me draw X here. Now, I draw the hemisphere around X. So all those points that's inside this hemisphere are neighbors of X, the cross neighbors of X. Okay. So this is the neighbor of X intercept Y. This is neighbor of X intercept X. Okay. Now, so we just have to verify some properties. So let's see why intuitively this will work. We have three properties to verify. First of all, the density, we should have n squared over 8 edges. Well, the inner edges are very sparse because the neighborhood just a little cap at the opposite position of X. This is like little o measure, negligible. So it's easy to see that the number of inner edges is little n squared. The cross edges is the one contributing to the edge density. If you have density 1, we will have n squared over 4 edges. But here, every vertex is adjacent to roughly half of vertices on the other side. So it's roughly adjacent to half of the vertices on the other side. So you have n over 4 times n over 2, which is n squared over 8 edges. Well, on the other side. Okay, so the first property is verified. Second property, the independence number should be sublinear. So independence number sublinear, why is this true? This is basically using isodiametric inequality for the real sphere, meaning that if you're given the measure, then the spherical cap minimize the diameter. Okay. Or the other way, maybe we should use yeah. Or given the diameter, spherical cap maximize the measure. Which way are we using? It's equivalent. We are trying to say if your measure is positive, they have 2 points far away. We are using this way. So given the measure, spherical cap, minimize diameter. So what it means is that whenever you take a set of size, this implies for any set A of size linear, then we can for sure find is this 2 points, two vertices, which correspond to 2 points on the sphere that are almost antipodal, almost at the opposite position. Antipodal, which then implies an edge, which is an edge. So the independence number is sublinear. Okay, then the last property that it's K4 free is some geometric intuition. Why this is K4 free? Well, first of all, K4 free is because both X and Y observe first that X and Y, they are both triangle free. Actually, they have high outgirth. High outgirth means no short odd cycles. Okay, this is because how can you have a triangle? Three vertices have to be pairwise adjacent inside. Adjacent means you have to go to the opposite. Now, adjacent to this guy, you have to again go to the opposite. But then these two are too close to be in the opposite position. Okay, so it's triangle free. Hand wavingly, this is the proof. Okay, now then how can we have a K4? You can only have like K4 with two vertices on each side. This implies K4 can only appear with two vertices on each side. Okay, but if you have two vertices on each side, like two vertices here, two vertices here, you have this is inner edge. They have to be in antipodal position. This is another inner edge, antipodal position. Antipodal means what? The distance, if this is unisphere, distance 1, right? Radius 1, the distance between x and x prime is almost 2. Let me write it here. Distance between x and x prime is almost 2. And here, if they are, if they adjacent in the cross as a cross edge, y lies in the hemisphere center at x. What's the distance between x and y? This is 1, this is 1, this is square root 2, right? So the distance is square root 2, close to. If the distance between x and y is less than, with some error, square root 2, okay? Let's say less than square root 2. Okay, so now the idea is basically that you cannot have x prime, let's say y prime forming an K4 because both of these two, think of it as distance at least 2. This is 2, this is 2. Think of them are completely antipodal, all right? Then we cannot have all the 4 sides. We cannot have all the 4 sides to be strictly less than root 2. So think for now. Is exactly 2. Then we cannot, because they are inner edges, right? Distance exactly 2. We cannot have all 4 red pairs at distance strictly less than square root 2. This is the geometric intuition. So that means you cannot form a K4. Let's see some details. Any question about the sketch? Okay, so here's what we do. We're gonna take, as I said, the vertex set will be uniform. The vertex is uniformly distributed over a high-dimensional sphere. So what's the dimension? Here are the details. I'm gonna first take K large, which will be the dimension. This is the dimension of sphere. Then we take a small number mu to be another small number epsilon that we choose over this square root. So epsilon is small. Okay. The first lemma is that we can cut the surface of the high-dimensional sphere into equal measure pieces, each of small diameter. So this is for us to distribute points uniformly over the sphere. So to distribute vertices uniformly over a sphere, we use the following lemma. There exists an absolute constant c bigger than 0, such that the following holds. For any sufficiently large n, which will be the number of vertices, as long as it's bigger than okay, this c might depends on delta. No, c does not depend on delta, I think. This is absolute constant c, but please check when you such that for any epsilon, for any delta, sorry, and for any n sufficiently large in terms of delta raised to the power k, the dimension, then we can cut the high dimensional sphere, k minus 1 dimension, into m pieces of same measure of the same measure. Here, we assume that we normalize the, okay, let me write in same page, same measure, each with diameter, and most delta. Okay. Here we assume, what's this high dimensional sphere? It's basically all points x in Rk, such that the each xi is xi not necessarily bigger than 0, just the sum of xi square. Do I use norm? Oh, right. Is 1 the little L2 norm? Oh, there's no I. Okay. And equipped with Lebesgue measure, normalized so that it has measure 1. The whole sphere, the surface measure, the whole sphere has measure 1. Okay, good. So now we can cut this. When n is sufficiently large, we're gonna cut. We take 2 copies, cut each copy into n over 2 pieces, and just choose an arbitrary point inside each region, each piece, to be a vertex. Okay. Good. Now, how we're going to define, as I said, for x, y, they are copies of, so this is a little bit vague. What I really mean is you distribute, using the above lemma, distribute n over 2 points on here. Okay, let me not write down the details. Now, x, the cross edges, the inner edges, if only if they are antipodal, so this means their distance, let me write in a shorter way, x minus x prime, take the norm, so that's their distance, is greater than 2 minus mu, the mu that we set up, this parameter. Okay. Some small number tending to 0. And for the cross edges, x adjacent to y, if and only if they live in each other's hemisphere, meaning that their distance, x minus y, is smaller than root 2, also minus mu. Okay. Good. Wait a second. Right. I think I made a mistake here. This should be square root, right? Well, let me just write this. Okay. Good. Anything else? This radius radius is 1, right? Let me check. Xi minus xi prime, if this is like 2 times xi. So sum of this square is, sum of xi square is 4. So that means 4, yes. Okay, good. Now let's prove these things rigorously, these 3 things. The first thing, there's nothing to prove. This basically utilize a lower bound on the spherical measure, since we just epsilon away from hemisphere. So you can get we just use lower bound on measures of spherical cap. Okay. And as I said, every vertex is adjacent to roughly half of the vertices on the other side. So n squared over 8. Now let's prove this one also. There's not much to say. Let me see. Right. So you basically use um, upper bounds on the spherical cap measure to prove, together with isodiametric inequality, to prove that there exist 2 points. So here we also have this isodiametric inequality plus upper bounds on measures of spherical cap. We can then get these 2 antipodal points. This is also not so interesting computation. Let me skip this part. So let's just prove that there's no K4. So we need to do 2 things. All right. No K4 means, first of all, each part is triangle free. So K4 can only appear with 2 vertices on each side. And we proved that you cannot have these. Here it's easy because we have exactly distance 2. But now we have a little bit room, right? We need to check that this geometric intuition it works robustly. So upper bound on this plus isodiametric inequality. Now let's show that it's K4 free. Claim 1. The induced graph X and Y each induces a triangle free graph. Okay. X and Y are symmetric, so let's just prove X. As I said, the proof, it's intuitive. If you are adjacent, X1, X2, you must go to the opposite side. But then where can X3 go? X3 is adjacent to X2. So you must also go to the opposite side. So let me draw this picture. You have X1 adjacent to X, adjacent to X prime. Then where can X double prime go? And these two are too close to be antipodal. So they cannot be adjacent. All right. Let's prove this rigorously. This is easy. Suppose we have a triangle. Let's call it X, okay. Suppose you have a triangle. Suppose X, X prime, X double prime form a triangle. Okay. Now let's look at sum of their distance. X, X prime square plus X prime, X double prime square plus this is writing like this is complicated. So let me change the labeling. Let me write X1, 2, 3. So suppose X1, 2, 3 form a triangle. Now sum of their distance. This is easier. What do we know? We know this is at least, this is inner edges. That means 2 form an edge if they are big, the distance is bigger than 2 minus mu. So we should have, this is strictly bigger than 2 minus mu square, and you have 3 of them, okay? And this can be computed, mu goes to 0, so 3 times 4, this is almost 12, right? On the other hand, this we can expand the right-hand side. The right-hand side equals to 2 sum of xi square minus 2 times their inner product ij in 3 choose 2 computation. Now let's get rid of this cross term, make it into a quadratic term by just noticing that x1 plus x2 plus x3 square equals to what? Xi square plus 2 times xi xj, right? Noticing this, then we can write this as 3 times the sum of xi square minus, now we change this to a square. Why we bother to change this to a squared thing? This is a norm which is greater or equal than 0. You subtract something. So it's m. You can drop this term. Okay. But each one of these lives on the unit sphere. This is unit sphere. So this is 1. 3 of them is 3. 3 times 3 is 9. You get a contradiction. 12 versus 9. Okay. So can we have 2 points on each side? We're now going to check that this intuition still works with 2 minus mu instead of exactly 2. Okay, this is suppose mu equal to 0 for a moment. Suppose mu equal to 0 for now. We show that for any mu, That kind of thing is impossible. So let's draw everything inside one sphere. Plane. G is K4 free. Draw things inside sphere. So we have 2 points from each copies of the sphere. So you have X prime, Y prime. Let me use different color. Y and Y prime. Okay. And we know that this is a K4 means it's almost antipodal, the inner edges for X and X prime, and almost antipodal for Y and Y prime. They are in the opposite side. And all these 4 pairs must be strictly less than. So this is a pure geometric fact. We want all 4 sides to be less than square root 2 minus mu. And 2 diagonal, we want 2 diagonal to be larger than 2 minus mu. We're going to show that this is impossible. All right, this is a lemma. Impossible to have 4 points. What do I use? Let's say x prime, y prime on high dimensional sphere such that you have this relation x prime bigger than 2 minus mu, y prime bigger than 2 minus mu, and this is the inner edges. We should have all 4 pair. Oh, all 4 pairs hard to write. So, okay, you have all the cross pair, x minus y, x prime minus y, x minus y prime, x prime minus y prime. All of them to be less than square root 2 minus mu. Okay. This is impossible. Using something like a parallelogram law, let's sum up all these 4 sides. If you sum up all 4 sides, let's first look at all 4 sides. X minus y squared plus x prime minus y squared plus x minus y prime squared plus x prime minus y prime squared. This equals to, if this is a parallelogram, we should have x minus x prime squared plus y minus y prime squared, right? Here are the 4 sides. Parallelogram means if this is a parallelogram, then it equals to the square of the 2 diagonal, which is x minus x prime, y minus y prime. But in general, if it's not, we have an additional term plus x plus x prime minus y prime square. Good. So since this is a square term, not negative, drop it, which is at least well, strictly larger because x and x prime, y prime satisfy that. So we have 2 times 2 minus mu square. If you do the computation, equals to 8 minus 4 mu plus some lower order term of order mu square. That's how we lower bound it. So now let's upper bound it. How do we upper bound it? Easy. We know all four sides satisfy that. On the other hand, left-hand side is less than 4 times square root 2 minus mu squared, which if you compute equals to calculation, I'll leave it for you, 8 minus a square root 2 mu plus big O mu squared. So this is a lower order term. Let's not worry about it. Leading term A is the same. Let's look at first lower order term. We subtract more here. So the upper bound is smaller than lower bound, a contradiction. So this proves that there's no K4. Any question? Okay. Let me briefly mention the most general definition form of this so-called Ramsey-Turan problem. So Ramsey-Turan density let's take first recall this definition of alpha sub p of g. If you take p to be a natural number, at least 2, let's say. This is just the p independence number. That's the maximum set of vertices u, such that u is a subset of the graph G, and G induced on U is KP free, P independence number. When P equals to 2, this is just normal independence number. We've seen this definition in the Erdős-Roger function, generalization of independence number. Now, we can then define the Ramsey-Turan number. The general form of Ramsey-Turan number take two numbers, natural number P and Q, Q larger. RTP of N, K, Q, M, let's say. What is this? This is the maximum number of edges of an n vertex graph that's KQ free. Where G is, it has n vertices and KQ free. So far, nothing very special, but in the Ramsey-Turan, we require its independence number being small. So instead of normal independence number, we require alpha P of G to be m most m. Okay. This is the Ramsey-Turan number. We can then define normalized things to get the density version, the Ramsey-Turan density. Rho P KQ is you first, as I said, the regime that we cared about is when the independence number is sublinear epsilon n when epsilon goes to 0, right? So let's first normalize this. Look at the edge density in this graph by n equals 2. By looking edge density, we need to take the limits when n goes to infinity, right? Now we want independence number to be sublinear. So we also want to take epsilon goes to 0. So this is sublinear. Take that limit. So this limit exists. It can be shown. I'll leave it as an exercise for you to show. So exercise, show that the above limit exists. So in this language, what we have just seen earlier is Samaridy's result. And Samaridy is basically saying, if you look at the K4 Ramsey-Turan density by looking at alpha 2, the normal independence number, this is at most 1/4. By passing to the limit and looking at density, we don't need then to work with this little o1, plus little o1 thing, so it becomes much cleaner. And Bolobash-Erdős graph says that you have the matching lower bound. So it equals to 1/4. Okay. But let me quickly mention that there is no Ramsey-Turan density. This the only known case is more or less in general, it's a hard problem, is when P equals to 2, so rho sub 2 of KQ. And for other graph, we don't know. No Erdős-Stone theorem in this setting. For example, it's still open whether K222, two blow up of a triangle, is positive or not. Okay. In other words, is there an n vertex K222 free graph with sublinear independence number, and it has positive edge density? No one knows if such graph exists. So for a long while, this is the only case is known, and also for a long while, it's been it was open for a long time whether the next smallest case is what? K rho 3 K5, whether this is positive or not. This is open. I claim that this is easy, so determine this one. If you look at alpha 3 independence number, K4 is trivial. So do this. The first non-trivial case should be K5. This is not known. Then about 10 years ago, there was a breakthrough by Joseph Balog and John Lenz, who proved that this is indeed positive. So what does this mean? No, what this means is that IE does there exist n vertex graph G, which is K5 free, alpha 3 of G is sublinear, meaning for any linear set of vertices in G, you must see a triangle there. And the number of edges is positive. The edge density is positive. Do we have such graph? About 10 years ago, 2010s, I don't remember, 2014 or 2012. You need to check. Balog and Lenz answer that yes, is positive. So the bound we have for now is rho 3 of K5 is at least 1 over 8. That's their result. And less than 1 over 6 and choose 2. 1 over 6. Okay. So what does this means? The upper bound? Upper bound means for any m vertex K5 free graph G with triangle independence number little o n, right? If its number of edges is more than 1 over 6 times n choose 2, then then the E of G is at most 1 over 6 plus little o1 times n choose 2. Okay, that's what it means. So let me prove this upper bound. Just a sketch. If you took my class this spring, this sketch should be easy to follow. You do regularity lemma on such a graph G, you get a reduced graph R. Then what we need to do is we need to show that R satisfies two things. First, it does not have triangle free. So, and another thing is the edge density of every edge in this reduced graph, edge weight, in R is at most 1/3. So triangle free already give you 1/2 and choose 2. And multiply by this weight together, you'll get 1 over 6 and choose 2. Okay. So why is it triangle free? It's triangle free is because if you have a triangle, if there is this triangle, then that means you have 3 clusters in this regular partition of G. They are pairwise dense and regular. So dense and regular. Then you can find a typical vertex here. Look at its neighborhood, which is linear size. And by slicing lemma, this is still regular. You can then find another typical vertex in the neighborhood of this, which has linear size neighbor here. In other words, we can find two vertices, x and y, adjacent, and they have linear size codegree here, right? But linear size codegree, what do we have? We have the graph has sublinear triangle independence number. Whenever you have a linear size set, there must be a triangle in there. So you will see a triangle inside. What's this triangle giving us together with xy? You get a K5. contradiction. This is why this triangle free. Why the edge weight is less than 1/3, this is also easy. If the edge weight is bigger than, let's say, 1/3 plus epsilon, then first of all, by cleaning, there are some vertices that are atypical to the other side. Okay, atypical means its degree to the other side is not around the density of this reduced pair. So you throw those away. These are little o(n) vertices. The remaining vertices, they are typical, and obviously there are linear number of vertices in this cluster. Again, by independence number condition, we know that you can find a triangle inside this linear size set. Look at their common neighborhood. Now, their common neighborhood is again, oh no, sorry. This is not what I want to say. You have three vertices forming a triangle, typical vertices, each one which has degree strictly more than 1/3, 1/3 plus epsilon to the other side. By pigeonhole, two of them then will share linear number of neighbors. So two of them, let's say these two, by pigeonhole. Okay. This then implies you have another triangle inside, you get K5. Very similar to the K4 proof. Okay. So that leaves us a gap. So this already was a hard question. I proved the easy side. This construction is some sort of product construction. The idea is some sort of product construction. Now, this was already hard. It was open for like 30, 40 years. And finally, a couple of years ago, I and Christian Ryer, Marion Sharifzadeh, and Catherine Staden, we together close this gap and prove that this upper bound is tight. So we have a new construction proving that the Ramsey-Turan density, this row 3 of K5, equals to 1/6. So this is a theorem. By myself, Christian Ryer, Marion Sharifzadeh, Catherine stated. We prove that row 3 of K5 equals to 1/6. So this is the first non-trivial case for the generalized Ramsey-Turan density. And our result is more general. It determines an infinite family. Let's focus on this baby case. And our idea is basically new version of Bolobash-Erdős graph using complex spheres. So our construction makes use of, before we've been using Euclidean real sphere, high-dimensional sphere. We're going to use complex spheres. Okay. Let me just briefly mention that in this Ramsey-Turan theory, there are two major open problems. In this Ramsey-Turan theory. One is this generalized Ramsey-Turan density for KQ, whether it's periodic, whatever that means, okay? Periodic. And let's not worry about that for now. And another major problem is to construct Bolobash-Erdős graph of other density. Bolobash-Erdős type graph with other density. So basically we answer that this is no. This is in our paper. LR S S. And here we can achieve all rational density up to half. Before, the Bolobash-Erdős graph has density 1/2, and this bound length construction using product construction can realize power of 1/2. This is some comments I want to make. So let's set up some basic properties of high-dimensional complex sphere to begin the construction. So what are the properties? Complex spheres. Now, let's again take K to be at least 1, and recall we've defined the real sphere. So now let's define the complex sphere, K-dimensional complex sphere. This is all the complex vector, unit vector, Z1 to Zk. Let me maybe use H. Doesn't matter. Each Zi is a complex number, such that the sum of the length of this complex vector is 1 unit length. This is the unit complex sphere. Okay. Let's recall also the standard inner product for two vectors. If you have x, complex number, x1 to xh, y, y1 to yh, then the inner product for two complex number, you multiply each coordinate xi with the conjugate of yi, I from 1 to h. Okay, in particular, the norm of x squared equals to the inner product with itself. And if you look at the distance between x and y, we can again compute the distance square equals to the length of x squared, length of y squared minus 2 times now the real part of x and y, their inner product. These are all very easy to verify. This is distance, square root of distance. Okay. Now, a very simple but useful property observation is that there is isometry between complex sphere to real sphere. So note that if you look at this mapping, now you have a h dimension complex vector, a point in the complex sphere, x, let's say x1 plus y1i. Now xi, yi, x1, y1 are real number. I is the imaginary number. xh plus yh times I. You can map this guy to just get rid of I and split xi, yi. This is a isometry. This is a distance preserving bijection. Round the h-dimensional complex sphere to 2h dimensional real sphere. 2h dimensional real sphere, right? Then all those counterintuitive, interesting properties of high-dimensional real spheres actually also extends to complex sphere thanks to this isometry. So thus, all those interesting and esoteric, strange properties of unisphere, a high-dimensional Euclidean sphere, we can use it for the complex version. Okay, right. And we again normalize the surface area, the measure of the complex sphere, normalize the Lebesgue measure to 1. That's what we will do. Any questions so far? Okay. So now let me describe the construction. I'll repeat it next time and prove the details next time. So let's first state the construction for row 3, 5. Okay. Let me see. We should take um, give me a second. Let me oh, strange. Right. Okay. So let's first take a cubic root, primitive cubic root of unity. This is little omega. That means omega cube equals to 1. If you want to write it, omega equals to the cosine of 2 pi over 3 plus I times sine 2 pi over 3. Okay, or write it in this way, e to the 2 pi I over 3. Okay, and what we will do is we're going to construct a near bipartite graph where you have little on square edges inside and edge density 1/3 across. That's exactly how we prove the upper bound in using this regularity lemma. All this triangle free and edge density of each edge weight of each cluster pair of cluster is 1/3. Okay. So how are we gonna do it? Let's take some parameter. So you have, let me see. Let's take some epsilon to be how many parameters we need? Capital K, yes. Let's take some epsilon bigger than 0, much less than 1 over capital K. Okay. And which is much less than 1. And we should think of the dimension h, which is the dimension of the sphere, tends to infinity slowly. And we will take, again, also parameters mu to be epsilon over square root 2h. N is at least c over mu over to the 2h. Now we're gonna, each copy of this x and y will be complex sphere now. Is h-dimensional complex sphere. how are we gonna, we again distribute points uniformly over X and Y. How the inner edges? Inner edges is easy. We have X is xi, xj. So let's say if these vertices are x1 to xn over 2, this is y1 to yn over 2. So xi, xj form an edge, inner edge. If and only if one is a rotation of another by omega, this cubic root. So what does that mean? So if your x is here, I multiply by omega, if you look at the complex plane, it's like rotating by 120 degree. So it's adjacent to some small cap, this 120 degree, rotate by 120 degree. It's adjacent to a small area here, okay? And another, rotate another 20 degree. So its neighborhood is roughly here, right? This is how you make the adjacency for inner edges. For cross edges, cross edges is a little bit more complicated. We have two x and y, okay? xi and yj. Let's say. We have xy adjacent to yj if and only if two conditions are satisfied. First of all, their inner products. First of all, their inner products, this is B. Cannot have two small imaginary part under any rotation of power of omega. Okay. A for any A in 3. The imaginary part, if you rotate by any power of omega, their inner product, xi, yj, I will draw a picture, cannot be too small. Must be at least capital K times mu. Second of all, their inner product, which is in the unit complex disk, must lie in this first 1/3 pie chart. There exists alpha. So let me draw a picture. First of all, note that xi, yj, for any I and j, their inner product, the norm is at most 1 by Cauchy-Schwarz. Okay, each one of which is a complex vector. So this is at most norm of xi, Cauchy-Schwarz. norm of yj, which is m most 1, which is equals to m most 1. Okay. So look at the complex unit disk on the plane, complex plane. What A is saying is that there's some strip we're going to exclude. This is a strip. Oh, this is too thick. Forget about these two strips for now. Just think of this power being 0. What does this mean? This is a complex number in the complex plane. Its imaginary product cannot be too small, so you cannot be too close to this x-axis. And multiply by power just means rotation. You exclude all those strips as well. Okay. The second thing is saying, if you look at their inner product up to a rotation, it lies on the first, this part. It lies here. So I'll talk about the details next time. Any question about adjacency? I go a little bit over time today. Sorry about that. Okay, so let's continue with more details next time. Thanks for listening.